talk, we have Ignacio Ruiz from IFT. So a very Madrid-centric seminar today. And he will tell us about asymptotic accelerator expansion in string theory and the landscape. Please take it away.
Okay, so first of all, I would like to thank the organization of this string finance session for allowing me to participate. And here I'm gonna talk about this paper we published last September with Jose Calderon Infante and Irene Valenzuela, which, as you see here, is called Asymptotic Acceleration Expansion in String Theory and the Swamp. Okay, so the title is pretty self-explanatory, but before starting, this is the structure that we're going to follow. We'll start with the introduction of why do we care about this problem, then introduce the setup, the theoretical framework in which we are going to work. Then we will introduce a new formulation for the Swampland de Sitter conjecture in terms of a convex formulation. Then we will have a detailed example of a possible potential, maybe evading this conjecture. And then we will wrap up with the result and some discussion. Okay, so the introduction. We know from experimental measures that our universe is expanding and actually doing so in an accelerated way. So two possible ways of obtaining this through a scalar potential is, first of all, we might be on a positive minimum of this potential, which would correspond to a positive cosmological constant, what we understand by dark energy. Or also it's possible that our scalars are running down some hill of this potential. This can either be local, so at some point it would reach a local minimum, or asymptotic, so it's moving through towards infinity, and it's not going to reach any minimum, it's just going to keep rolling and rolling. As we will argue later, we're going to be interested in this asymptotic quintessence scenario. Okay, so how do we get this accelerated expanding universe? So for this, we just consider some homogeneous Franklin-Metto-Robinson-Walker universe, which is populated by some scalars, phi, that have a kinetic term from which we can identify the moduli space metric in the kinetic term and also a scalar potential. One can obtain that if one is working under slow roll conditions, so that the potential is dominating over the kinetic terms and also the friction term coming from the Hubble parameter dominates over the second order terms. One obtains that this accelerated expansion happens. Okay, so if we have this accelerated parameter that we define here being smaller than 1, this can be written in terms of the norm of the gradient of the logarithm of the potential and the geodesicity of the trajectory that we are following along moduli space. On principle, we see from this equation that if this non-geodesicity was very large, then as it's going like 1 over this non-geodesicity squared, we would have a very small epsilon, but we will see that actually the solutions that we obtain are geodesics. So in this scenario in which we are moving along geodesics, we find that by introducing this de Sitter parameter, which again is nothing but the norm of the gradient of the logarithm of our positive potential, we will find accelerated expansion if this value is actually smaller than 2 over the square root of d minus 2, where here d is the number of space-time dimensions that we are working in. So we will try to study this in the asymptotic case. Why do we care about asymptotic accelerated expansion? First of all, because through it, we will be moving along asymptotic regions of the moduli space in which, for example, these correspond between other cases, for example, low small coupling or large volume. So we would have a good parametric control, but as we will see later, there are other possible limits. Also, we will be dealing with runaway potentials. For example, those obtained from string theory share very universal behavior, such as an exponential decay. And also, we will not get into this, but for phenomenological implications, having an eternal accelerated expansion can pose some problems for our universe. So, on principle, just by looking at this action, we could say, okay, we just will come up with some potential and modulate this metric such that the de Sitter parameter is small enough so that it allows for an accelerated expansion. However, as we I guess most of the audience is used to, we could wonder if such EFTs that we can come up with are UUV complete. This is, they can be embedded in a consistent theory of quantum gravity. This is where the Swampland program comes, specifically in the sense of the Swampland de Sitter conjecture, which is motivated by the seeming difficulties that one finds when trying to obtain stable de Sitter vacua in string theory. And this motivates the Swampland de Sitter conjecture that says that the Sitter parameter needs to be larger than some order one value, CD, that on principle should only depend on the dimensionality of our spacetime. And regarding the value of this CD, we have several lower bounds. We will discuss the strong one, which is motivated by dimensional reduction and also observables in these kind of scenarios. And as you see here, it would prevent an accelerated expansion of the universe, and also the TCC1, which is motivated by trying to prevent subplanckian modes from re-entering the Hubble horizon as the universe expands. As you see here, it's smaller than the strong one. So in principle, even if we fulfill the TCC version of the Swampland de Sitter conjecture, we will find that our universe on principle could be accelerated while fulfilling this bound. Okay, so in several papers of the literature, this conjecture has been tested on several potentials, and they all have passed. But the thing is that they are a pretty small subset of all the possible potentials, because they either work on weak coupling large volume, or they just consider one moduli or one term of the potential. So we could wonder if we could do better. We could consider more general asymptotic limits and find tools to study these potential and their solutions. Because of this, we will introduce our setup, which we will be working in 4D, n equals 1 supergravity. We will obtain it through compactifying theory with fluxes on Calabi-Yau fourfold. And by looking at the scalar part of our supergravity action, we find again what we introduced before. We have some scalars with a kinetic term and a potential. These scalars will be complex. We will separate them in an axion and saxionic part, and will correspond to the Kahler and complex structure moduli of our Calabi-Yau. We will focus in the case that we are studying the complex structure moduli. Coming from the F-theory compactification, we see that the potential comes from the flux compactification, where V is the volume of our Calabi-Yau fourfold, and G4 is the norm of these four-form flux, and G4 is just a topological term, which will be set by tadpole cancellation. And from the Kahler moduli, in which the Kahler potential, in which both the volume and the complex structure enter, we will obtain our metric. So taking into account that this metric will enter both into the obtention of this potential and also the model space metric, we will see how these complex structure moduli will appear in both the metric and the potential. So on principle, this potential and metric would seem very complicated to compute, but actually by using some machinery from mathematics, specifically in mixed Hodge theory in asymptotic limits, we see that we can simplify the above expressions. The mixed Hodge theory we apply to these kind of potentials from flux compactification. Here you have a reference in which it's explained in pretty good depth. What we do is classifying our different asymptotic limits, in which we send several saxions to infinity in some like growth sectors. By classifying these possible limits, we will obtain a potential which has a power-like form, and also a metric, in which these Li's and Di's are just set by the kind of asymptotic limit that we are studying. We see here that in the potential, the axions come in these squared mass-like terms, and the saxions come in like a more general power-like expression. So as we will see later in the example, the axions are stabilized by the subleading terms of the potential, so we will only need to focus on the saxionic trajectories of our solutions. So In order to go to infinity, it's not the same as just having a single moduli, a single section. There's just one way to send it to infinity. But if we have several moduli, we will need to specify the trajectory along moduli space that we are following towards this infinite limit. We will obtain through the trajectory. And from in the slow roll regime that we introduced earlier, one can obtain that the equations of motion result on the sections following gradient flows. That is, they will move along the directions along which the scalar potential decreases faster. As we saw before, in order to check in order to see that only the gradient of the potential affects the asymptotic expansion of the acceleration of the universe, we would need to check that these trajectories are indeed geodesics. We can see that from the potentials and metrics that we had before, the general trajectories that we obtain are have this power-like behavior, and indeed it can be easily checked that they are indeed geodesics, so we don't need to worry about this. And once we have this trajectory, which depends mainly on the power of the different way they expand towards infinity, we will obtain that the de Sitter coefficient, which is nothing else that minus the derivative of the logarithm of the potential along our trajectory with respect to the canonical distance in moduli space, only depends on the beta and the metric of our trajectory, with beta is these exponents of the trajectories. Okay, so on principle, once we have this potential that we want to obtain the gradient flow solutions, we can have two scenarios. The first one, and that's the one that is mostly discussed in the literature, is the one in which we have a single dominating term, which decays along any direction going to infinity, as you see here, the family of solutions that has a specific beta, nonetheless features a continuous family of parameters. So there are like infinitely many ways of getting to infinity. The other option is having several competing terms that not necessarily all of them decay as we go to infinity. As such, for example, this one, there are some directions in which each of the terms can decay or blow up. This way, one obtains a value of the potential or an attractor, which is unique and given in terms of the coefficients of the potential. And as one could imagine, on principle, having this value, which is obtained by the competition between the terms, can give way to flatter directions than the one we would obtain by a single dominating term. Okay, so on principle, we could just consider a potential, a metric, and try to solve the gradient flow equations and compute the de Sitter coefficients, but we're going to see that we can reframe this problem through a convex hull formulation, study this Swampland de Sitter conjecture. The convex hull formulation is nothing new in the Swampland conjecture. It appears in many others, but as we will see, it's a little bit different than other previous explanations. So it's not difficult to show that the gradient flow trajectory can be computed from an optimization problem where we define these de Sitter vectors, which are nothing more than the gradient of the different terms of the potential when we have several of them, and we just apply the Vielbein of the moduli space metric so that we go to a flat frame. Here we have that T is an modulus 1, a unit vector, by which, using the inverse Vielbein, we can recover our trajectory in moduli space. We recover the tangent vector, and from it, we can recover our solutions. This optimization problem can be understood as first obtaining the terms of the potential which decay slower, so they will be the dominant ones, and of these terms, we will obtain the directions along which our trajectories decay faster. This way, the solution of the optimization problem can be understood as the distance between the origin and the convex hull spanned by these de Sitter vectors of the potential when we have several terms. This motivates to a rephrasing of the distance of the DS conjecture in terms of that the distance between the origin and the convex hull of said de Sitter vectors need to be larger than an order one a number that should only depend on the space-time dimensionality. And as before, if you want to prevent asymptotic accelerated expansion, dCd needs to be larger than 2 over the square root of d minus 2. As you see here, we have the different terms of the potential coming here, and we can classify them in 3 families. First are the light ones. This is the ones we have a positive components or positive components of in the de Sitter vectors. These are terms of the potential with decay as we go to infinity in any direction. The opposite ones are the heavy ones in which we have negative components of these de Sitter vectors. These terms blow up irrespective of any asymptotic direction that we take, so we will not want them because they will blow up in any direction, so they would prevent going to an asymptotic limit. And finally, the most interesting part, which are the resembles, in which we have both positive and negative terms, so they will blow up in some directions and decay in some others. This is the ones we will be more interested in. Here we have several pictures in which you can see what we mean by light rest in the convex hull. As you see here, when we have 2 moduli, the light ones are the ones we have all positive. So first quadrant, the heavy ones is the third quadrant, and the rest the second and the fourth. So here we have that in the first 2 pictures, we have that all our terms are light, and we can have 1 or 2 moduli competing, or 2 terms competing, but nonetheless, in this case, they correspond to the de Sitter conjecture being fulfilled. We can also have competing terms between 2 rest terms, but once, while for the light terms, we needed them to be very small in order for the de Sitter or the distance of the convex hull to be very small. It's not difficult to see that we can have that the dominating terms, their associated de Sitter vectors, they can be very large, so not close at all to the origin, but nonetheless, the distance to the convex hull, it can be very small. So here we have 2 possible. Here, both of the dominating terms are rest ones. Here we have 1 rest on light, and here we have that they both violate the de Sitter conjecture for this value of CD. And nonetheless, with these rest terms, one could obtain non-admissible solutions, because as you see here, one of the tangent vector components is negative, so this corresponds to this second suction being sent to 0, so not getting to an asymptotic solution. So using this framework that we have introduced, we can study a specific example, which is realizing type 2B at weak coupling a large complex structure. This can be realized by the F-theory compactification of the flux on a Calabi-Yau fourfold in the terms of the Hodge theory notation. This would correspond to a 2 or 1 to 5 to 2 limit. Regarding the metric, it has the U and the S 1, 3. 2 minus 1 is 1. 5 minus 2 is 3. So we would have this kind of potential. We would have both light, rest, and heavy terms, and also this constant topological term that we will have set to 0, but there's no topological abstraction in doing so. So regarding the suction, they can be more or less dominating. They will dominate more in the asymptotic regions as they are more heavy, but the axonic functions that accompany them are such that as we move towards more and more dominant terms, we will obtain a partially ordered chain of functions in which, to go to the following one, we will derivate with respect to some of the actions. This means that the more dominant terms will be accompanied by just constant axionic functions, so they just will depend on fluxes, and we can set several of them to 0 so that we set several of these functions as we want to 0. This means that these functions come squared in the potential. We will have that the first subleading term, the rho, will be linear, so when squared, they will correspond to a second degree equation that we will have a minimum, which will stabilize the potential, the action. So as we said before, we will only need to worry about the suctions. So the solution that we want to study is the one in which we set these raw functions to 0. We can obtain this by setting the several NSNS or Ramon fluxes to 0, so that we have these dominating terms of the potential. These are the dominating ones. The axionic functions only depend on the fluxes, and the actions are stabilized by values. This corresponds to this quadratic solution that, as you see, is a single one, because we will be dealing with a value of the potential by these competing terms, and the specific solution is set by the value of these non-zero fluxes. And once that one computes the zeta parameter, it obtains that it's smaller than both the TCC and the strong bounds of the de Sitter conjecture in 4D. This can be easily realized in the convex full formulation. So we have that our dominant terms are both rest terms. So they are not specifically close to the origin, but the convex full that they span is actually small to the origin. By computing its distance and direction by which this the convex hull is faster approached, we obtain both the distance corresponds to the Sitter parameter value, and the direction corresponds to that taken in moduli space. Here we have this sublime terms, which will be the ones responsible of stabilizing our actions. In our paper, we actually study a lot of different potential in different limits, and we comment to them like whether they stabilize the moduli, whether there are some flat directions, etc. And apart from this type 2b limit, we also study type 2a in Calabi-Yau threefolds, which is the mirror dual, which corresponds to a large volume, and the moduli that we study there are the Kahler moduli, as opposed as the complex structure one that we study here. And also other F-theory limits. We do not have a direct type 2a or type 2b string theory interpretation. Again, unless we are dealing with the mirror dual, we will be dealing with complex structure moduli, which, as we will comment on later, can be interpreted as a small caveat to our analysis. So to be finishing, what we have obtained here, we have just discussed a single of the examples, but there's another one that result in asymptotic state expansion. One is, as we have explained, type 2b with coupling, a large complex structure. It's smaller to both the TCC and the strong bounds. And we have other F-theory limits, which is F-theory limit, which is not necessarily weakly coupled, in which the potential is asymptotically given by this expression, and the de Sitter coefficient that we find is larger than the TCC, but smaller than the strong bound. So on principle, it would allow for an accelerated expansion of the universe. As you see here, in both cases, we have that our terms have both a positive and negative exponents in the different terms. So they would correspond to the rest terms in scenario 2, where we have several terms competing. From the convex hull interpretation that I explained earlier, it's easy to see that our solutions will be more likely to feature small de Sitter parameters if the dominant terms are res ones. Again, these res one and scenario 2 correspond to single trajectories, so it's a good thing that just by having the fluxes, we will have a single trajectory, as we will know the values that the moduli will take in their journey to infinity. And while here we just have considered two sections, one could easily generalize these to more moduli by simply using these convex hull formalism. Previous no-go results that were derived in the literature were implicitly assuming that we were just working with a single term. So scenario 1, this I didn't explain here, but it's more detailed in the paper. These arguments do not apply when we have several terms competing. As I introduced earlier, we have a small caveat that we were just considering a complex structure moduli. So what happens with the Kahler moduli? In type 2b, they are not stabilized, and we need to stabilize them, because if they weren't stabilized, it's easy to compute that the jitter coefficient would be larger than the strong ones, so we wouldn't have an accelerated expansion. For phenomenological reasons, phenomenologically reasons, if we want to avoid fifth forces, we would need to have this scalar moduli stabilized. But how to do this is complicated. We would need to consider quantum corrections, so we have them stabilized at the higher hierarchy of our potential. This might or might not be difficult to obtain. And as I said before, in type 2a, in which we are working with this scalar moduli, we can stabilize the complex structure, but on the two moduli limits that we have studied, these examples are not featuring asymptotic accelerated expansion of the universe, but we don't have any argument against having this for more general, more suction limits. So in principle, that was something that one could try to obtain. And for future directions, as I said before, the straightforward thing to do is consider more limits. We can assign them through asymptotic Hodge theory. The more moduli that we have, the more possible limits that we will obtain. At some point, we will cease obtaining diagonal metrics, which are super easy to work with. But on principle, once we have these metrics, we can obtain the field line, and we could just work with the convex thematic in the same way as before. So one could imagine that the more moduli we have, the more potentials that we have. And in principle, through one possible thing to do is having a systematic study, either by some computer program or something similar, to these all possible limits and potentials that we can obtain in different by having more moduli and turning on and off the different fluxes. Also, the Kahler stabilization of the stabilization of the scalar moduli needs to be addressed. It might involve corrections or working in the non-asymptotic regime, so we would go away from what we have been working with. And finally, it's true that here we have obtained gradient flow, slow roll, geodesic trajectories. So one could wonder what would happen if we would consider more general solutions, which are like, for example, a non-gradient flow or a geodesic. There's also like the problem of having non-geodesic trajectory maintained as we go to infinity, but that's another problem. Finally, so the take-home message is that even though the DS Swampland conjecture might very well be true, there are very good arguments for it. It's not as straightforward to show for general potentials as it may seem. More work needs to be put into it, either by multifold potential, how to stabilize the moduli, or the different solutions that we have to find. So I hope that the audience was excited by these new possibilities and wants to work with it. So with this, I finish, and thanks for the attention.
Thank you, Ignacio, for the great talk. Other questions? Yes, please, Fabio.
Hi, Ignacio, thank you for the talk. So I have a general question about your assumptions, because at the beginning you said that you use the slow roll approximations to get epsilon with the gradient. But typically when you have the same number of scalar fields as the number of the scalar potential terms, and you get epsilon as a constant, so a power law scale factor, the kinetic energy is not parametrically suppressed with respect to the potential. So this doesn't seem to be compatible with slow roll.
We checked into this, and it's true that for several of the examples that the potentials we obtain, it's true that the slow roll conditions didn't seem to be compatible, but for the examples that we feature, the ones with the small de-Sitter, they are actually like slow roll. The ones in which the slow roll condition was lost usually featured larger gammas, larger de-Sitter parameters. So in our case, for these examples that we've shown, they are indeed slow roll solutions.
Okay, but so So by slow roll, you mean that the kinetic energy is smaller than
Yes,
the
the
potential
potential.
energy, but not that. So it's, in other words, minimizing the gradient of the potential is not the same as solving the slow roll equations. Do you agree with this?
Yes. But in this, if we assume that our potential is larger, and actually we checked once we recovered the solutions, and we also have the friction term dominates over the second order terms, which actually by having that we are along geodesics, we fulfill this. We have that indeed the gradient flow solutions are indeed coming from the equations of motion.
Well, so I don't understand. So if you cannot neglect the second derivative terms in the Klein-Gordon equation, then that's not a gradient flow, right?
Yeah, but we checked that from the solutions that we obtain, the second order term it can be disregarded because the trajectories that we find are geodesic, so they are indeed much smaller than the Hubble term.
But the parametric dependence on time is the same, right? So it's not. So it can be numeric. Maybe the kinetic term is numerically smaller, but
maybe it's not exponentially smaller, but it's numerically small enough so that in our approximation we consider that these slow roll are actually like solutions. But once you obtain it and you check it back, it works fine.
Okay, thank you.
Marco?
I had a question about the quantum corrections to the potential.
Michael, can you?
Okay, sorry.
I think Marco was first, and then Tom.
Okay, thank you. So I have a question, Ignacio. So which is the interest in getting accelerated expansion geodesics that satisfy the de Sitter conjecture for phenomenology?
What's the interest?
What is their interest?
Okay, no. So in principle, it would be very a good case that having very non-geodesic trajectories, because as you see here, if the non-geodesicity is very large, this term here is much smaller than 1 because it's the -1. So we could have this very small thing, the deceleration parameter. The thing is that there are several papers that suggest that as we move to asymptotic regions in asymptotic trajectories, these trajectories should not be geodesic. So in principle, it would seem difficult to obtain non-geodesic trajectories that are sustained as we go to infinity. In our case, we checked our solutions, and they indeed, through the moduli space metric that we obtain here, they are indeed geodesic. So that term just goes to 0, and the acceleration of the universe just depends on the gradient.
Yeah, that's precisely I ask you this question because in fact I know that by using like a non-geodesic trajectory you can make still like the lower parameter small. That's why I ask you like which is the interest in getting an accelerated expansion that is geodesic and that satisfies the de Sitter conjecture, because it means that you get like an epsilon that is too big for observation. Right?
Can you repeat that?
You get an epsilon if you have a geodesic. If you have like a trajectory that satisfies the de Sitter conjecture is geodesic, so you cannot make the epsilon, the lower parameter, so small to be compatible with observation. If your interest, if your interest is just like to see whether like at this region you can get just accelerated expansion, is fine. But just to become just a theoretical interest. That's why I ask you like for phenomenology, which is your interest? Because
okay. So at first it's just that there's this de Sitter conjecture. That's at first it says you cannot have accelerated expansion. You might not have accelerated expansion, which is compatible with quantum gravity. So the examples that have been tested were not very simple, but were a very small subset of the set of all possible potentials. So our goal was just to check if we could more or less easily obtain parameters which would be close, like small enough to have this expansion. It's true that they are not directly compatible to the measure observations, but as we said, this is just 2 examples that we obtain from having just 2 moduli. On principle, we could repeat this procedure to have for more general limits with more sections. So on principle, even though the values that we obtain are not directly compatible with the observations, there's nothing against having this possibility, like having the small enough values when we consider like 3, 4, and 10 potentials.
Okay, thank you.
Maybe in interest of time, Tom, if you can make a question short.
Thanks. Yeah, I actually just have a comment that I think it's not quite right to say that that past works have only considered the case of a single term. So in particular, in my paper that you referenced, what I pointed out is that in type 2b, there's this universal coupling of the dilaton, such that far out in the dilaton moduli space, you automatically will satisfy the convex hull condition. So the challenge is you have to somehow find a way to approach an asymptotic regime in complex structure moduli space while stabilizing the dilaton.
Of course.
And I think there's another argument too, which you're familiar with since we're working on a project together on it. But the emergent string conjecture and sharpened distance conjecture, if true, suggests that any infinite distance limit is going to have that has accelerated expansion is also going to have either a decompactification or some string scale that becomes lighter than the Hubble scale. And so to come up with an example where you have controlled accelerated asymptotic expansion in 4 dimensions, I think you'd also need to violate the emergent string conjecture, which maybe is possible. I don't have a proof of the emergent string conjecture, but I think it's worth noting that there's I guess other prices to pay for getting accelerated expansion even with multiple terms.
Okay, yes. First of all, here we are assuming that some of our moduli are stabilized, but also so regarding previous papers in the literature discussing, like, given I think the one you have in mind, the thing here is that when you have several terms competing, such as here, the thing is that the trajectory that is actually followed by the by the scalars following this gradient flow of the potential are not the same as, for example, if we would have if we would consider what do you mean? I think I don't have exactly here, but your argument, I think, the gradient, like if you have just one moduli, if we consider you have a moduli, the gradient flow of both the potential and also like the modulus of the super potential is the same, but once you have several moduli, they are not the same. So when you compute the gradient, you have, apart from the parallel term, you have also a perpendicular term, which is not 0. So in this case, I think that we can discuss this later. Once you have more terms, the argument is not straightforwardly generalized to more moduli. So I don't know if that was what you were wondering.
Can I?
Yeah.
Sorry. Yeah, I think maybe this is a good point where we can continue after we end the recording. And so let's just thank Ignacio and also Roberta again for the excellent talks.